So welcome everyone. On behalf of Ultra Forensic Technology, I'd like to thank all the participants for joining us for this online event. There's many of you from all around the world, and we want to take this opportunity to recognize the special circumstances that we are all facing. We sincerely hope that you and your coworkers, your friends and families are safe and are doing well. We're glad to spend time with you today to show you what we've been working on. We felt that it was important to have this online event this week, which corresponds to the original week for the annual AFTI meeting, where we could have interacted with you in person, or many of you anyways, in person. And we look forward to doing so at the postponed meeting in October. In the meantime, here at Ultra, we're hard at work to continue bringing you innovations for a safer tomorrow. There will be four speakers today. My name is Michel Paradis. I am a product manager at Ultra Forensic Technology. I've been with the company for 17 years, working on IBIS, our flagship product, and now on this latest product that we are launching today. With me are two of my colleagues. First, Andy Boyle. He's held multiple positions at our company over the last 26 years. From IBIS instructor to firearm researcher and subject matter expert for the research team. In the last 8 years, Andy has leveraged his extensive laboratory and firearms experience to act as our liaison for the Interpol Ballistic Information Network. Working closely with Interpol, Andy travels the globe educating, initiating, and promoting the benefits of the IBIN program to firearm experts and administrators. My other colleague is Dr. Danny Roberge, who joined our company 20 years ago. He holds a doctorate in physics for optical pattern recognition. He was awarded a fellowship for a postdoctoral project related to optical fingerprint identification and biometric encryption. He's currently a senior scientist in the research and prototyping group and has developed and implemented algorithms related to the acquisition and correlation of bullet and cartridge case images for IBIS. He is the author and co-author of several patents in the field of automated ballistic identification. Last but not least, it is our privilege to have Ron Nichols as our guest speaker from Nichols Forensic Science Consulting. I'll let Ron introduce himself as he starts us off with a perspective on greater objectivity in the firearm and toolmark identification. Ron?
Thank you, Michelle. Good day, everyone. As Michelle shared, I am Ron Nichols, president of Nichols Forensic Science Consulting. And for those who don't know, I've been a forensic scientist since 1984 and a fully trained firearm and toolmark examiner since 1991 with the Oakland Police Department, the Bureau of Alcohol, Tobacco, and Firearms, and now my own training and consulting firm. Throughout my career, I have been actively involved in efforts to better articulate the scientific foundations upon which this discipline is based. I've done that through numerous publications, including a book looking at that very issue. I have also done it through training lectures and workshops, both in person and online. My goal has been to educate examiners in the scientific foundations of the discipline and provide training in how to better articulate those foundations. When evaluated and articulated in a correct way, the scientific foundations of the discipline are sound and valid. Now, that correct evaluation and articulation hasn't always happened, but when it has, the courts appear content that the foundational premise of the discipline, that is, different tools produce different tool marks, is a valid premise. At the same time, the courts have concerns that tend to be repeated over and over, including, what is the chance that another tool could have made this tool mark? Well, the AFTI theory of identification says something about a practical impossibility. Can you define that, asks a court? Let's be honest. As a community, we have been pretty much unable to answer that question to the court's satisfaction. So as a result, we now have the court telling examiners what the court would be willing to hear. One example is to a reasonable degree of ballistic certainty. What does that mean? I don't have a clue. Or how about this example? More likely than not. Yikes, we know that can't be true. But then again, since we can't provide the courts with an answer they will accept, I can't really blame them for writing the narrative for us. The courts have two basic repeated concerns. The first is that the subjective interpretation of pattern correspondence renders the final source conclusion unreliable. And the second is the lack of a statistical database for the conclusion that two tool marks share a common source. Let's face it, better articulation does help, but what is needed is a technological solution so that these ongoing concerns can be put to rest. And that's why I'm excited to be a part of this event. I was introduced to the Quantum 3D microscope in Montreal and can say with the utmost confidence, it will help us to respond to these two concerns. As you view these presentations, it will be important to recognize the value of virtual microscopy, which permits greater standardization of the work. Topography is no longer visualized using transient lighting conditions as in a light comparison microscope. It is measured and permanently stored. The comparison conditions are reproducible, offering greater repeatability and much better review and verification of not only the conclusions, but the thought process underlying those conclusions. It also permits remote collaboration, allowing examiners in different locations the ability to collaborate. Also, pay special attention to the quantitative model, which will provide graphical depictions of similarity scores, which offer greater objectivity when the separation of common source conclusions from known non-matches is clearly depicted. Included in this is a discussion of false match rate that you will not want to miss. With quantum, we are positioned to retake that narrative from the courts because we will not only have greater flexibility, but we will have and demonstrate far greater objectivity than we ever have, including an opportunity to answer that question, what is the chance another tool could have made that tool mark in a way that has a court saying thank you instead of saying, hey, what?
Thank you, Ron. The quantum 3D microscope is indeed our answer to the challenges you just described. The quantum 3D microscope, as people are starting to hear that name a few times today, it's a new product for firearm and tool mark identification. It's intended to provide firearm and tool mark examiners with the best 3D visual and quantitative tools for common source determination. Fundamentally, the 3D microscope allows you to acquire, view, and analyze tool marks. It captures the details of the surface topography and the shape of objects. It gives experts the visual and quantitative capabilities for comparing marks. This includes statistical modeling to provide a false match error rate for striated marks on bullets. And the first quantum is specialized for bullets, but it's also useful for other objects and tool marks. So the major components of this 3D microscope include the 3D topography acquisition equipment and its associated software, interface and controls, a 3D comparison viewer, which completes the basis for the 3D microscope with powerful but intuitive features. The special ingredient which Ron Nichols hinted at is the quantitative analysis, where we look at for objective results. And to tie it all together, we have the application that lets you organize and share all the information. Quantum is powered by IBIS technology. This is because some of the Quantum's design is inspired from our experience with IBIS 3D technology. But we've adapted it to a new purpose, and we've augmented it with additional capabilities. Quantum is designed for casework involving more direct examination of questioned objects. And it can also be useful for various studies of toolmarks. To get started, I want to give you a quick glimpse of the quantum application and its workspace organization as a starting point for the other components presented later today. For example, if you have to create a case for firearm identification, you create a workspace. So the 3D acquisitions of questioned items would be captured into the workspace. The acquisitions can then be viewed in a comparison viewer. Those comparisons can be recorded in screenshots associated with notes. A comparison viewer screenshot saves the exact viewing state so that you can return to it later and continue from where you left off. Quantitative analysis can be performed on the bullets, and the results are recorded in the workspace. The application is designed to be flexible, to adapt to all types of work and approaches. There's much more to the application, so it's just a taste I'm giving you today. I'll explain more, though, at the end of the presentation about data management and data sharing. Next, Andy Boyle presents some of the acquisition capabilities of the 3D microscope and how effective 3D comparison viewing can be for casework and other types of examinations. Andy?
Thank you, Michel. So I will be showing you the 3D acquisition component as well as the 3D comparison microscope component. So when it comes to working the acquisition, the first step you have to do is mount your object to be entered into the machine. And so to do so, we have a diverse set of stubs that can be interacted with your object. And each of those stubs, when combined with using sticky wax, gives you that versatility to be able to align whatever that object is to be optimally positioned underneath the camera sensor. So an example of how that would work would be for a bullet. We have a specialized mounting jig that is designed to align a pristine bullet so that it has very little wobble when it's first entered into the machine. And you can see here, the jig is designed here to have that shaft go directly above where the bullet is aligned. And we can watch that process actually in action right now. So here you have the bullet being placed face down underneath the shaft. The stub is then mounted onto the shaft with a bit of wax in its nose. That's pressed into the bullet itself. And once that's raised out, you can see that that's been aligned with very little to no wobble to that bullet. That whole process took about 18 seconds to do just by gauging the length of the video. So it's very quick and easy to set up those pristine bullets to be positioned into a quantum system. Pristine bullets aren't the end of the story, though, of course. When you're dealing with fragmented shapes, whether it's a deformed bullet or partial jacketing, the best way to do those would be a freehand method involving the wax and the side of the nose of the stub. And we can see that for this sample here. Here's an example of how that would work. There you have the stub and a little bit of red wax. That's going to go on the side of the nose of the stub in line with that indentation mark on the stub. And now the exhibit itself is simply placed in the wax, and you want to align it so that the base of the bullet is square, and from a side view, you want the top of that surface to be as flat as can be. And that, with a bit of practice, can be done very quickly. That only took about 6 seconds longer than the previous one. We're under 25 seconds for that mounting process. And so once your object is on one of these stubs, they could then be placed onto the motorized shaft at the front of the quantum unit. There's a door that opens, presents the shaft to the user. The stub is placed on there, that gets retracted back into the machine. The door closes again, and that means that no ambient light in your room is going to affect the data capture of that surface. So there's also the opportunity to mount other objects. You're not restricted to just doing bullets, of course. Examples of what those could be, cartridge cases have several areas that can be of interest to get a view of under a 3D microscope. And that would be great for looking at chamber marks, ejection port marks, extractor marks as well. Anything on that body of the cartridge case, anything on the side, can be lined up and imaged in 3D in the quantum system. That could also be done with metal samples, or more likely casts of those samples could also be set up on the side of the stub using that wax. And you can line that up to do things such as plier marks, screwdriver indentations, tool marks that fit that sort of dimension can be placed, the cast can be placed on that stub for 3D imaging as well. So to set up an acquisition, we have a series of tools in the acquisition unit to make that go very fast and easy. There are pilot cameras that let you see the exhibit from 2 different angles. There are auto centering tools, there's auto focusing tools as well. And most importantly, there is intelligent surface tracking to cover oddly shaped exhibits. And we can see what that would look like with this example video here. Let me just pause this for a moment and tell you what you're looking at. What we have is this oddly shaped, in this case, it's representing a bullet that's had some deformation. The black dot that you see here is the center point of the rotation motor shaft. So this is where it's going to be rotating from. And during the acquisition, there will be 3 main things taking place. It will be rotating the exhibit. It will also be translating the exhibit across this horizontal plane, and it will be making Z adjustments on the focal plane up and down on the Z or Z axis. And so what you will see when I press play again is that there will automatically be adjustments made by the software to always ensure that the area about to be imaged by the sensor is perfectly perpendicular to that camera's axis. All of that is being done by the software on autopilot. Once you tell it where to begin, you can press record and it will do that job on its own. And you see this dividing line here, that center line, that's important because you have the thin line here of where the machine still has to go. You have the thicker black line showing where it's been. During each scanned area, there will be a 50% overlap between new information and previously acquired information. And that's done deliberately so that half of the image, when this stitches the images together and that overall mosaic grows, every time it's stitched an image together, 50% of the content from the last image and the new image are common to ensure that that is a smooth and proper growth of the overall image mosaic. And so this is almost done its rotation around, and that is how it effectively navigates around an odd shape. So to give that a real world example, here's that piece of jacketing that I mounted in the previous, or a couple videos back there. On this surface, we can see 2 of the land impressions. There's a land impression right here. There's another one on this side. There's one that's just over here. So there are a total of 3 that can be done on this deformed fragment shape. So let's see how that would take place. I'll pause this right away. Now, the acquisition window is open right here. And the first thing that's about to take place is the mouse. If you can see the little white mouse icon, it's already on this button. When this is pressed, there will be 2 new camera views opened up of the 2 pilot cameras. Let's see that happen right away. And within this image now, you've got a left side view and a right side view of that exhibit. And now the green dot that you see within both photos, that is telling you where the actual acquisition camera is looking at this time. There's no information in here because we are way off of where the light is reflecting strongly. So we have nothing but blackness to see here, but in the pilot camera, I can see exactly where I want to go, and my mouse is already up there. I'm about to click 2 little indicators on where I want to go. Let's watch that happen. There's an indicator, there's another, and once I press that centering button, it goes straight to that area identified. Turn up the light, and now we are looking on the surface of the bullet. A little click and drag moves it to the side, adjust the focus, And now up in the top here, we're going to rotate that exhibit until the top of that first land engraved area, or LEA as we call them, or Lee. That first Lee is now at the top. I'm going to slide it into view. And we are looking at the top shoulder of that first Lee. And when I hit the next button in just a moment, right now it's going to do a quality check on that area. And during that quality check, it's actually adjusting for perpendicularity. It's doing a scan of that surface. It's reading how the alignment is set up. And if it deems it necessary, it will make an alignment change, which it just did there. So now it knows where to begin. Let's go tell it where to end. And it's going to rotate along. Right now, this advancement is just being done with the mouse wheel. So your finger is just rolling your mouse wheel along, and that rotation is taking place until the bottom shoulder is now at the apex point. You simply slide that back underneath the camera, adjust the focus, and now we are looking at the bottom shoulder of that third land impression. We can see here on the side that whole distance that we've traveled. This is where we set ourselves to begin, and it's going to go over here and end in that area. If I hit finish, it does that same quality check on the bottom area, the end area. It's doing a surface scan right now. It's going to gauge the shape of that surface in relation to the camera's axis. It will make an adjustment if it deems it necessary. And now we're allowed to start the acquisition. So it knows where to begin, it knows where to end, and it will navigate between those two all by itself. And this advanced repositioning mode, this option here, that is the intelligent surface tracking. So because of the deformation on this surface, it will need to make adjustments on the horizontal plane from time to time. And the machine will compensate for that in real time during the actual acquisition. So here's the first scan at the beginning. It's going to compute that, make an advancement, scan again, autofocus, auto light, scan the surface. And once that second scan is completed, we will start to see the overall surface begin to grow over here. And it will continue doing that as it transitions from that start position to the finish position. For the sake of time here, let's just jump ahead a little bit. We can see the progress that we've made so far. The first Lee is done. The second Lee is almost done. There's that bottom shoulder. That will appear in the next scan. It just did. Now let's jump ahead a bit more. Now we're almost at that end position. We've got all of one, all of two. We're halfway through number three. And if I jump a bit more, now we are looking over the surface. One, two, all of three is done as well. And so with it reaching the end, it's going to begin to compile all that information together. That's what it's doing right now. It's doing the compilation of all of that. It's reading the signature, and it is also going to set the anchor lines in their initial state. But once it's done that, the validation screen will open up where we get a chance to look at the surface that was just scanned for the first time. And so here it is. What we'll do now is, here's your shape view in this area. This is your surface view. This is a flat plane view of what was just acquired. And we're just making adjustments to the sensitivity of the 3D on the surface. And now that it's been enhanced, we can play with the side light and interact with those shadows, place the anchor lines where they should go. This one's being set for the bottom shoulder of the first land engraved area. This is where we began our acquisition. And so once those anchor lines are fine-tuned, we can call this Lee 1. This second one is Lee 2. And the third one is Lee 3. Fine-tune the anchor lines there, which hadn't been done yet, and then do the check mark to finish the acquisition. You have the option to eject the subject out of the quantum as well. And if you look at the timestamp here, that process of the deformed acquisition, 1, 2, 3 land impressions, that took less than 9 minutes to image the surface. Let me close this. So that is that deformed shape acquired. And now we can take a look at what that shape actually looks like in 3D. Here it is again, Lee 1, Lee 2, Lee 3. And up in this area here now, we have that 3D shape representation of the scan that took place. And you can see that the metal is no longer perfectly pristine. It's also got a little bit of a twist to it, but it wasn't difficult at all for the machine to capture all of that in that surface scan as it went through the recording process. So that's a deformed bullet acquisition. We can take a look here at some other shapes that I got the machine to acquire. I wanted to test out that surface tracking. I wanted to put it to the test and have it go around some odd shapes. And so I worked with what I had available, and just looking at these stubs there, stub number 5 for the mounting stub has some uniformity to it between two edges, but it also has this giant sort of hump back here. And so I just placed that underneath the sensor, hit record to see if it would make its way all around that surface. And in fact, it did without any issue at all. So this is just an example of how that surface tracking can always maintain that perpendicularity over a surface as it navigates around during the recording. Here's an older type of bullet mounting stub that we've used in previous versions of IBIS. It's got that flat wall here, a little step, some curvature, step down again, another flat wall. And once again, that automatic surface tracking made its way around that shape. By this point, I was looking for a challenge and came across a bottle cap that I had somewhere in the kitchen. Looking at that ridged outline of it, I wanted to see what would happen there. And I told it where to start, where to end, and it was able to navigate around that shape, which involves quite a bit of different surface topography within that if you take a close look at it. However, it had no trouble making its way around that all on its own. Lastly, I was starting to get a little creative. I thought, well, why not try to do a cartridge? So I have a 9mm cartridge here, and I simply put some wax on the side of the body of the cartridge case, push that into the nose of one of the mounting stubs, set this up, and it would acquire that flat surface all the way across, right over that lip of the mouth of the cartridge case, onto the bullet surface, around the ogive, all of that. It had no trouble navigating around. So that is, once again, just that surface tracking, handling some odd deformed shapes without any issue. Let me just pause this one here for a second. This was quite interesting because that center rotation point was right about here. And so if you think about it, this whole shape here, the whole nose of that bullet, as it was rotating, it was doing quite a wide swing. But by combining that rotation with the horizontal slide of translation, the machine is able to always maintain that perpendicularity, and it had no trouble working its way around that shape. Calibration, of course, is a very important step with this. If you're going to have this as a 3D microscope, you've got to be able to prove that the measurements are in fact correct. And so the traceability measurements can be done using two ISO 17025 certified targets that are in each quantum system. So one of those two targets is a bullseye that is used to confirm that the 2D target measurement is correct with the pixel size that it is acquiring at. So there is a known value to everything in this target. The system acquires it, and the end result of that acquisition should be in line with what the known value is. Combined with that 2D target, there's also a sinusoidal wave 3D pattern that can be used for confirming the 3D is accurate as well. And that works off the roughness detail here. And of course, these as ISO 17025 certified targets, their values are known, and they are compared to the acquisition values that the quantum system completes. That's one method you can do using what's inside your quantum system. You're also, of course, free to validate this with your own independent calibration tool, should you have one. And in that case, you would acquire that calibration object on your own, and then you could export that data for your own validation of it externally of the quantum system. And that means that you would use X3P format, which is a standard format for 3D data, to export it, and you can work with that and validate your quantum machine independent of quantum, should you decide to. now we get to the 3D microscopy portion. And so when it comes to doing your comparison work, there are a lot of dynamic viewing tools available inside there for a variety of objects. And examples of some comparisons that we can do, here is what it would look like doing bullets with cut rifling. And in this case, we have a pristine bullet compared to that damaged sample that we just acquired. So let's take a look at that. And I'll just pause it for a second here. Michelle showed this this image already, but what is about to happen is we're going to choose one of these as our reference image, the other as a test, and then we'll open up the comparison viewer. Reference and test are selected, comparison viewer is opened, and now we're in a side-by-side mode here. So let me just pause it for a second. What we're seeing on both sides here, on the far left, you have the full representation of that reference bullet. What disappears right down here, if you can see it, it says L4, that's land engraved area 4. That immediately reappears up top here. So you have an infinite loop that is available here. On this side, you only have a partial area because of the damaged nature of that surface. We have land impression 1, 2, and 3. And by default, they're simply lined up Li1 to Li1. Now, what we're going to do over here is select the depth grayscale image overlay. And what that gives us, in that depth grayscale view, you have the raw 3D present. And that raw 3D is represented by the shade of gray of each individual pixel in that image. And while it looks a little cloudy to the human eye, the system is actually able to see with pixel point precision the exact nature of the topography based on the shade of gray of everything in that pattern. And big bold marks will appear as big white or black lines in that surface. So play some more. Now we're adding 3D rendering. That makes it a little more palpable to the human eye. 3D elevation is going to enhance some of that surface information to make it react better to the side light. And now here, we've just found on that test exhibit a nicely marked area there. There's a strong feature right here that we're going to use as our guide. And on land impression number 2 here, we're going to start looking for that feature somewhere on that reference bullet. And what you see between these 2 pink lines here, that is what is showing up larger in this middle section. So I'll press play some more, and we will move that reference exhibit to try to find that strong piece of information that appeared on the test Li number 2. Now that looks promising. Line him up to the hairline in the center. And we can play with that side light, work those shadows in real time. You see there's no lag to how that's worked. Now I'm just going to pause it for a second here, because that deformation, when that jacketing was damaged and it was bent in an exaggerated curvature, more so than its pristine original nature, that caused this particular land impression to have its information get kind of squeezed together. And that makes it a little difficult. We're almost perfectly aligned right in the center, but we're slightly offset at the top, and we're slightly offset at the bottom as well. And what we can do with a tool here called Stretch is we can temporarily make an adjustment to that surface to compensate for that deformation that took place. And here you see in that center image, we're stretching it out a little bit to make up for the fact that when the metal was bent, it compressed that area. Now we are looking at the pair of leaves in the phase above, and this is interesting too right now. That damage that happened on the surface here ultimately bent the metal in a way that it exaggerated the angle of the anchor lines on that test exhibit. The reference has a fairly normal angle to what you'd expect from a pristine bullet with a right twist rifling. This one here, the twist is appearing exaggerated because of how the metal was bent when it was deformed. And what we can do to compensate for that is use a tool up top here that's called Adjust. And when the Adjust tool is applied, it takes the angle of those anchor lines and corrects them to horizontal, and it corrects all the information between them to horizontal as well. And that just makes it easier to interact with that. Here we can reduce that stretch because it wasn't the same amount of compression that happened on that pair of line engraved areas. Play with that side light, and then lock the reference so that we move him and they both move. Take a look at that second pairing again under the horizontal conditions, and look at the third pairing as well. So there's something interesting all the way across this one in this particular phase. And now this viewing so far was all in the surface mode. Now we're going to look at the shape mode with the original shape of both exhibits. And so there's your reference, which is still a pristine round surface. You have the test. And let me pause this for just a second. The deformation that happened on that test makes it difficult to compare them side by side in the shape viewer. But now to compensate for that, in the video now, we've just done a right click on that pristine reference, and we're about to select a tool called Clone Shape. And now Clone Shape will take that reference and force that curvature onto that test sample. And we'll see that right now. So this is giving you a chance to remove that deformation from that fragment for the duration of this comparison. And now we can play with the tools here, adjust the 3D elevation, play with that light angle now to see those shadows stronger. There's that strong feature in line impression number 2 again. And we'll go looking for that feature here. And now slide the dividing line across, bring him over, and you can do an alignment here as well. Once you're happy with that, you can go over and adjust the light angle once again, experience how those shadows interact with that surface. You could zoom in as well more, zoom in, zoom out. Those are all tools available for you to interact with. So that was a comparison between 2 cut rifle bullets. I can give you an example now of what a comparison between 2 polygonal bullets can look like. Here you have them opening up in the comparison mode once again. Go to the depth grayscale, enhance the 3D rendering, enhance the surface elevation, and now just looking at these 2, the test exhibit seems quite a bit smoother than the reference, at least in the way the default alignment has them as Lee 1 to Lee 1 as it's first opened. So we'll start to look around for a good, strong piece of information to work with. And now on that test, there's some strong stuff up here towards that driving shoulder, that top shoulder. So now let's take that as our standard and see if we can find that on the reference exhibit. And as we come around, that starts to look pretty interesting in that format. Bring it over to the hairline, zoom in a little bit, and interact with those with the side light to experience how those shadows really make the surface appear. And now if this is a true alignment, we should be able to find something else hopefully along that phase. And as we bring these ones along, we've got a pair now here. This is now line impression 6 to 4, looking very good. And you can see there's some strong damage that took place along the top there. It skidded against something while being test fired. But if we go now to the shape view, we can see them again. There's that patch that had contact with the water tank, most likely. And we can move that position over, slide the exhibit, make some adjustments on the alignment, and play with the side light once again. And this gives you that chance to interact with those shadows and see what there is present between those 2 exhibits. Moving away from bullets, we can take a look now at what's on the side of the cartridge case. Some chamber marks here. These are between 2 different Makarov pistols. And what I like to do with this one, we'll do the usual composition, 3D rendering, 3D elevation, and then just looking at the surface here, this feature caught my eye. And so I'm about to grab that and bring it down to the center point using the reference, slide him down, and now that's what I'm going to look for as I move this other one around. And once you line those ones up between these 2, you can see that that agreement is quite strong. And it's not only in that one little area, but as you rotate these around, this continues around the entire circumference near the mouth of those two cartridge cases. Play with those side lights. Once again, go to the shape viewer, look at them with the original shapes. And you can bring these ones around to look at in one of those areas more closely. Lastly here, let's take a look at what a pair of ejection port marks would look like. Once again, we'll choose our reference, choose our test, open the compare screen, and now we have two, these are from two 45 auto cartridge cases. And right away on the reference, I see what I want to take a closer look at. There's my chamber, ejection port mark. Make some 3D adjustments. And now on that test, let's take a look and see if that shows up anywhere. Bring these guys closer to the hairline now for more in-depth comparison. Play with that angled light, see how those features interact. And we can even zoom in a bit more as well. And that is a comparison between two ejection port marks. So as you can see, you're doing the 3D microscopy, you have the tools necessary for a fast dynamic evaluation there between different objects. And it's extremely quick to work with. So that concludes my portion. I'll pass you back to Michelle. Thank you very much.
Thank you, Andy. So with all this detailed 3D topography at our disposal that Andy showed you, the natural next step is to use the reliable 3D measurements to feed correlation algorithms and statistical models. New methods that produce error rates bring more objectivity to common source opinions. So next, Dr. Danny Roberge will present some of the theory behind the quantum objective model, as well as some practical analysis scenarios. The quantitative analysis module is currently specialized for bullets with conventional rifling, but we plan to expand its capabilities as quantum evolves. Now, before Danny starts, you'll hear him talk about objective identification and something called an RBL graph. I say rebel graph. That's my way of calling that graph. So I just wanted to explain what RBL stands for. It stands for Roberge, Beauchamp, and Lévesque, the three authors of the published paper that Danny will refer to. He'll refer to that in his segment. So Danny?
Hi, everybody. Thank you, Michelle. Quantitative analysis. So let's start with the ballistic identification fields observation. Currently, and that's a fact, there's a lack of scientific basis for ballistic identification. And secondly, any ABIS system, automated ballistic identification system, should acquire topography 3D information. And just like biometrics, fingerprint identification, iris pattern recognition, and DNA sequencing, ballistic identification must be supported by a probability of making a bad call. So we have an excellent IBIS searching tool. It can serve as the basis for comparison system with the quantitative component, so it made sense to develop it. So we started to work on a model in 2016. We presented the first result at the FT conference in 2018. FT is for Association of Firearm and Toolmark Examiners. Same year, we presented an international conference on pattern recognition and artificial intelligence. And over more than 100 speakers, they chose 10 of them to write a paper in a special edition, and we were actually picked. So in 2019, we published a paper in the International Journal of Pattern Recognition and Artificial Intelligence. And the reason why we published that paper is because we wanted to show to the community that objective identification is feasible with reasonable pixel size and high resolution. In 2019, again, we resolved a strong actual problem that we call subclass misidentification using quantum. We presented at the FT meeting in 2019, and here again, I think results were well received. If you want to have a copy of that paper, you only have to write the title in Google, and you will end up on the World Scientific webpage where you can click on the left corner and have your own PDF version since it is open access. You have all the detailed motivations, and you have all the equations of the model behind the objective identification within that paper. So my talk will be split in two portions. The one on the left is the theoretical portion. We will talk about the difference between the actual IBIS system and the new application Quantum 3D microscope. We will see the model that is behind the objective identification. And on the right portion, we will actually try to play with that. We will do some practical scenarios. We will try to solve 2 simulated murder cases, and we'll finish with the Grundy MB proficiency test. So let's start with the difference between the IBIS tool and Quantum 3D microscope. Here we recognize the IBIS family products, and these products provide gun crime investigative leads. We are actually looking at a needle in the A pile. And to do that, we need to be really quick, really fast. So we need fast correlation algorithm, but the question is how fast? Well, as an example, we perform 1 billion correlations per month in the United States only. So we need to compare with a lot of agencies. We need a lot of connections where the NIBIN network. The Quantum 3D microscope. Well, Quantum assists expert conclusions for common source determinations and testimony. We can see it that way. You have IBIS search that actually find the needle, but Quantum actually describe the needle in detail. Within Quantum, we have a high quality virtual comparison microscope, and Quantum gives the capability to quantify the strength or the quality of a match. More technically, in IBIS, we don't want to reject any match. So we minimize what we call the false negative. In Quantum, we don't want to accept any no match. So we minimize the false positive. So 2 different goals, 2 different correlation algorithms. So to summarize, in IBIS, we search through really large data sets. So speed is definitely an issue. We provide a list of correlation score, but the score itself doesn't mean that much. It's really the rank. In Quantum, we are most of the time working with casework, 1, 2, 3, 5, 10 bullets at a time, definitely local search. So accuracy here is really important. That's the issue. And that accuracy will allows us to quantify the error or actually have the chance of making a wrong call. In Quantum, we have measurement traceability and acquisition unit certification. So Quantum 3D microscope, we actually have 3 steps. The first one is the acquisition with the certified acquisition unit. Secondly, we have visualization in 2 modes. The first mode is the surface mode, where we are looking at the detail at the micron level at the surface of the bullet. This is what we call the roughness. It contains the relevant correlation information. Or we may have the choice to look at the entire shape, where we have the overall shape, the waviness, and the roughness. And finally, the error estimation through the objective identification that we will explain in detail in the next few slides. So the chance of making an error or making a bad call is the probability that a system incorrectly identifies a pattern X with pattern Y. This is the false match rate that we intend to evaluate for ballistic identification as well. Now, we're going to see the model that's behind the objective identification. That portion is a little bit rough, but it provides all the tools to understand what is behind that. So either we have a pristine or a deformed bullet. We always have 2 pieces of information. The first one is the 2D information that we call reflectance. The other one is the 3D information that we call topography that we split into level of resolution. First one is the waviness, which is the overall shape right here. And that little crispy detail right here is the detail on the micron level, like we just said. And this is the roughness. And this contains the relevant correlation information. So from now on, we are going to use only the roughness for our analysis. So this is, I would say, the on-road carpet of the surface of the bullet. What we do next is we find the anchor lines, the white lines right here, and we isolate all the land engraved area automatically. Now, as a reminder, here we have a phase view of a barrel. We can see all the rifling inside the barrel where we have lands and grooves, and by pressure, when the bullet goes through the barrel, the lens is engraved inside the bullet. So this is the name land engraved area. And this is where the marks correlate the most. And this is why we focus our attention on that region of interest. So now we go back to the land engraved area. We do some, we call anisotropic filtering that isolate the ballistic information right over here. And from that, we extract the most relevant lead profile. Now, firearm examiners are looking at these profiles in two different but successful ways. The first one is they are looking at the global similarity of these two profiles. What we're doing pattern matching. So this is why we derive a pattern matching score. The other way is by looking at all those little lines that we call stria. They're looking at the consecutiveness of matching stria. So this is what we call doing line counting. So this is why we derive a line counting score. So we have two metrics that characterize the correspondence of the similarity between two bullets. So we will take those two metrics and we will present that on a 2D graph. So now we have our metrics that actually represent the similarity between two bullets. Now we need data to do statistics. So we need to acquire bullets. We had access to a data set of 136 firearms conventional rifle. We had in total 406 bullets where we have pair, trios, 4, and even 5 bullets per firearm. But in total, we had 422 matching pairs that I personally looked individually using the virtual comparison microscope. And I marked the one that I could identify because I don't want to train the system with something I cannot identify on a microscope afterwards because it will pollute my training process. So I ended up with 235 visual matching pairs. And I have done that prior to any digital collation. So without any further detail, here's the results. This is the objective identification graph. On the horizontal axis, we have the normalized scores, pattern matching score that is between 0 and 1. On the vertical axis, we have the line counting score that is a score normalized between 0 and 1. And as an example, if I click over here, I have the two profiles that I'm actually comparing. The pattern matching score gives me 0.75, which means physically you have 75% global similarity. And that makes sense. Now I'm looking at the location of the stria for both of those patterns. And by comparing those stria location, I derive two other metrics, the density of matching stria first, and the number of independent group of matching stria. And I derive a line counting score of 0.5. So pattern matching score is connected to global similarity, and the line counting score is connected to stria location pattern matching. So we have two different philosophies, two different schools of thinking in a unique graphic. So now we go back to our distribution right here. The black distribution right here is for non-match score, and the gray one is for the visual matching scores. Here we have 80,000 on matching score for that one, and 235 visual matching score for that one. Intuitively, we know that separation line should be somewhere over here. But more systematically, we are looking at the direction of those visual matching score, and we actually project all of those score right here on that axis, and the length of that yellow vector is officially my objective identification score, D. Why we define D? Well, it's the distance between the origin and the tip of that yellow vector right here. And as you'll see, as we increase that distance, well, the visual matching agreement gets better, grows stronger. And finally, looking at the statistics of that score, it actually collapsed the problems to a 1D problem. So we end up with those two distributions. The gray distribution on the left, this is the non-matching objective identification score D distribution. The one on the right, the white one, it's the visual matching objective identification score D distribution. And now we set a decision line. And I'm defining that any pair of bullets that generate a score above that decision line will be considered as matching bullet. And by taking that decision, it has a consequence. We introduce errors. These are non-matching score above that decision line. This is my false match rate. That's the probability that two bullets will be by mistake identified as being shot by the same firearm. And we can actually have that piece of information in my objective identification graph. So here again, we have on the horizontal axis that matching score. On the vertical axis, we have the line counting score. We have the separation line right over here that's split between the non-match distribution and the visual matching distribution. Now, if we look close to the middle, we can see actually 8 little dots. These are non-matching scores that are above the decision line, the separation line. But we have 80,000 non-matching score below the decision line. So we have a ratio of 8 over 80,000. This is a ratio of 1 over 10,000, which is 1 over 10 to the 4. So this is why we label the separation line with a 4, which means that it corresponds to a false match rate of 1 over 10 to the 4. That line right here corresponds to a false match rate of 1 over 10 to the 6. that one over 10 to the 8, and so on like this. So now, if I take two bullets, for example, and I call it, the collation score is right over here on the ISO line of 6. The location of that score, we can actually draw two conclusions already. The first one is that this pair of bullet is likely to match visually on the comparison microscope because we trained the system that way. As soon as you have a collation score above the decision line, you have visual similarities. Secondly, the location of that score right here, it tells me that there's only one chance over 10 to the 6, means over 1,000,000, that two non-cis bullets generate a score like this. This is my false match rate. This is a number that you can actually bring in court. And finally, as you will see, that graphic is amazing for casework analysis and proficiency test resolution. Okay, now we are at the last slide of my theory portion. If you understand that slide, you understand quantum and you can actually use it. So we take the example of two bullets, B1 and B2, that we actually pre-align with the best alignment. As you can see here, you have strong strata matched together. Here again, we have 6 pair of leads. We have 6 scores. These are the scores for each individual pair of leads. And now I have a pretty decent question. What is the overall bullet comparison score? Well, to answer that question, we rank the score, those scores right here, from the highest down to the lowest. And the option we do have is taking the highest score, taking the average of the 2 highest scores, maybe taking the average of all the 6 scores. So we ran the simulation for taking the highest scores, the average of the 2 highest scores, and so on. And surprisingly, we ended up with 2. Taking the average of the 2 highest score actually optimizes separation between the 2 distributions. And this is what we want to do. We want to optimize that. So finally, quantum, the final score is the average of the 2 highest scores. So the final graphic will be like this: pattern matching score in the horizontal axis, line counting score on the vertical axis, a separation line right here that corresponds to a false match rate of 1 over 10,000. And here we have an average of 0.9 and 0.8, which gives me 0.85. And because that score is way above the decision line, physically it means that we have at least 2 pair of leads that will visually match within those 2 bullets. Now, what if I had 0.4 instead of 0.8? Well, the score would drop right over here. It's much lower, but it's still above that separation line. In fact, in that area, we have 1 pair of leads that visually match. So the location of those correlation score in the graphic tells me a clue of what to expect on the virtual comparison microscope. And we're going to use that all the time. So from now on, we have all the tools to understand quantum. And as you'll realize, everything is about that graphic, because actually it provides the false match rate, which is the number that creates the bridge between the forensic lab and the court of justice. Okay, let's jump in the practical scenarios. Here we have a body, and from the autopsy, we extracted 2 bullets that by definition, they are a piece of evidence. We have a question firearm. We bring it to the lab, shoot in the water tank, and have 5 test fire. Now the question is, if I actually acquire all those bullets in quantum, can I connect this question firearm to those pieces of evidence? Before going any further, why 5 test fired? Well, we strongly believe that 4 or 5 test fired is a minimum to cover most of the expected variants and marks of the question firearm right here. So best practice would be to actually have a minimum of 4 or 5 test fired. So this is the interface of quantum, where we have all the 7 bullets of our case. And we have 4 boxes on the right here. We have the unknown box where we actually drag the piece of evidence because these are question bullets. You have the 3 known box right here that are actually connected to different question firearm. So as an example here, we drag the piece of evidence in the unknown box, and we drag the 5 test fired within the known 1 box right here. So we have this right over here, and as we click, okay, the software is performing all the cross correlation. In that case, it takes all the bullets from the unknown box and calling them all together. And since we only have 2 bullets right here, it generates only 1 score. In the known 1 box, now we call it test fired 1 against 2, 3, 4, and 5, 2 against 1, 3, 4, 5, and so on. So we will generate 5 times 4, and we divide by 2 because score is symmetrical. It means bullet A and B gives the same score as B and A. So in that case, we generate 10 scores. Then we have, of course, the cross correlation. Every piece of evidence will be correlated again, those 5 tests fired. So I will have 5 plus 5. So I will have 10 scores. So in that case, I will have 10 plus 1. I will generate 21 scores for 7 bullets. Maybe I don't want to see them all. So at the end, we have the option to filter, to do some visual filtering. I will show you some example and you'll understand pretty quickly. So first thing to do is to look at the question firearm. If your question firearm doesn't mark well, you don't have any case. Okay, so it's really important to actually get the signature of that question firearm. So first thing, we call it the first test fired against the 4 others, the second against the 4 others, just like we did. 5 times 4 divided by 2, because score is symmetrical, we generate 10 scores. Now, if we click on known against known, so we are actually just visualizing collation score for test fired. So we have our 10 score that actually are the question firearm signature. This is a cluster that is way above the separation line, which means that question firearm marks pretty well. So for every comparisons we have like here that involve 2 bullets, well, those 2 bullets has at least 2 pair of leads that visually match. That's what it says. The firearm marks pretty well because the cluster is way above the separation line, and this is my question firearm signature. If I click on that correlation score right here, it involves test firearm number 2 and 3, and I have the 2 pair of leads with the highest score right over here. And as you can see, we have strong similarities on both pair of leads. Okay, now, same thing with piece of evidence. We only have 2 pieces of evidence. We generate only 1 score. So we will only have 1 score on the objective identification graphic. That score is way above the separation line, which means that physically those 2 bullets will have at least 2 pair of leads that will visually match. And as a matter of fact, all the 6 pair of leads looks pretty similar. So far we have our question firearm signature. We have 2 bullets that match pretty well. So now we have to do the cross correlation. Now we clicked on piece of evidence 1 against known 1, which is against the 5 tests fired. So we generate 5 correlation score. So this is a cluster we have right here. We click on piece of evidence 2. Here's about the same cluster right here. So what can we conclude? Well, all those 5 comparisons again, if you look at those 2 bullets at a time, they will show 2 pair of leads that visual match minimum. And physically, the piece of evidence 1 and 2 compared to the test fired behaves exactly like if you were comparing the 5 tests fired together. By looking at the lowest correlation score, we can say that there's only 1 chance over 100 million, because it's 1 over 10 to the 8. 2 non-sister bullets generate a high score like that. So we can say that piece of evidence 1 and 2 were shot by the question firearm, and the chance of making a wrong call is 1 over 10 to the 8. Now, by clicking that point right here, it highlights the fact that this is piece of evidence 2 and test fired 3. Clicking again, it highlights the scores for that matching score line counting score. And we have the option to go on side-by-side view with the best match, and it automatically aligns the pair of leads with the highest score at the best alignment. We can have a look at the shape at the same time. And since it is digital information, we can split that information in 2 levels of resolution, like I explained before. You have the waviness, which is the circular shape right here, but the roughness is the detail at the micron level that contains the relevant correlation information, and nothing impedes me to increase the importance of that roughness for visualization. And if you look closely, I would just double the importance of roughness. Now we can actually bring the bullet close to each other and have a zoom in. And as you can see, this is really convenient compared to a standard comparison microscope. Okay, now let's jump to second case. We have the body, actually the same, and we extract 1 bullet from the autopsy. So we have 1 piece of evidence. In that case, it's different. We have more than 1 question firearm. So we have question firearm number 1, test fired 1, 2, 3, and 4. We have question firearm number 2, test fired 1, 2, 3, and 4. And question firearm number 3, test fired 1, 2, 3, and 4. And here again, the question is, if I'm acquiring those 12 bullets plus that one, can I connect one of those firearms to that piece of evidence? This is my interface. This is my data setup right here. And like the other case, I drag the piece of evidence in the unknown box. I drag the 4 test fired of the first question firearm in the known 1 box. the 4 tests fired of the second question firearm in a known toolbox, and the 4 tests fired of the third question firearm on the known 3 box. So this is what I actually do have. And by clicking OK right here, the software is performing all the cross correlations. So I will have a lot of correlation score. So this is my visual filtering window. So nothing is clicked yet. Okay. So the first thing, exactly like the other case, I want to see how my question firearm marks. I want to get their signature. So if I click on this, so I have the 4 tests fired of the first question firearm. The same formula, 4 times 3 divided by 2 provides 6 correlation score. And this is my question firearm number 1 signature. Cluster way above the separation line. Question firearm number 2 generates 6 score as well because we have 4 tests fired. And question firearm number 3, 6 correlation score as well. As you can see, those 3 question firearm marks pretty well because they provide cluster way above the separation line. Now, if I click to my piece of evidence, I will correlate that against known one where you have the 4 tests fired of the first question firearm. I will generate 4 correlation score. And those scores are way below the separation line. In fact, it is overlapping with the background distribution that is the known non-match distribution. So those scores behave like non-matching score. So we can say that piece of evidence wasn't shot by the question firearm number 1. We click that one. So piece of evidence with the 4 tests fired of the question firearm number 2. So we generate 4 scores. And here again, it's way below the separation line. So piece of evidence wasn't shot by the question firearm number 2. If we click that one, it's generating 4 score again because this is against the 4 tests fired of the third question firearm. But those scores right here, 1, 2, 3, and 4 are way above the separation line. Clicking at the lowest correlation score, now we have piece of evidence was shot by the third question firearm, but the chance of making a wrong call is 1 over 10 to the 7 because it fits right in the middle of isolant of 6 and 8, so we assume that it is around 7. Visual inspection. Piece of evidence, question firearm number 3, first test fired. Now, as you can see, there's a lot of stria matching together. That pair of leads, that one right here. And second test fired. As you can see, there's strong agreement. Okay. That pair of leads corresponds to that one actually. Okay, now the last practical scenario that is quite interesting. This is the branded MB data set. Those tests are shipped to forensic lab to evaluate 2 things: the expert skills and competency, and the discipline's error rate. Physically, it is a set of 35 bullets that were shot by 10 consecutively manufactured barrels. But within that group, we have 2 sets. The first one is the training set, where we have 10 pairs of bullets, 1 pair of bullet per barrel. Barrel 1, we know that 1A1B was shot by barrel 1. Barrel 2, 2A2B, barrel 3, 3A3B, and so on like this. So we have 20 bullets in the training set. Then we have another set that we call a testing set, where we have 15 unknown. And the challenge now is to find out from what barrel each of those unknown have been shot from, and to actually submit a key that has that format. Barrel 1, we know that shot 1A1B, and we found out that it shot unknown D because it matches with 1A1B. And we do the same exercise for all the barrel and submit the key. So we want to do the test by collating each unknown with the entire training set right here. The way to do this is to drag all the 15 unknown in the unknown box, and to drag all the training set in the known one box, and click the button and do all the collation. And in the visual filtering, only clicking that box right here, that tells that we correlate unknown A against the known one that includes all the training set. So we will generate 20 correlation score, and actually 2 of them are above the separation that involve unknown A with 9B, unknown A with 9A. So we can actually assume that unknown A was shot by barrel 9. We click on the second unknown. That will be correlated against all the known one, which is the 20 bullet of the training set. Here again, 20 correlation score. 2 of them are above the separation line, unknown B3A, unknown B3B. So we can say that unknown B was shot by barrel 3. And we keep going like this. With C, we have 10B, 10A. With D, we have 5A, 5B. And we actually created the key like this. Unknown A, barrel 9. Unknown B, barrel 3, so on. So we submitted the key. We can actually stop the exercise right over here. But this is what we have so far. But we didn't correlate the unknown yet. Maybe we will have some extra information or something to validate our key with that. So if we click on that, it will correlate the first unknown against the 14 others, The other unknown gets 14 others, and so on. So we will generate 15 times 14 divided by 2, 105 extra scores. And if we look at on the objective identification graph, we have 2 clusters. That one is not really interesting because these are pairs of unknown bullets that were shot from different barrels. But that one is really cool. These are the pairs of unknown bullets that were shot from the same barrel. And if you click on that one, it involves A and S. It means that A and S are connected together. And if you come over here with the key you have so far, as a matter of fact, A and S were shot by the same barrel, barrel number 9. You have those 3 scores right here that involves L, V, and W, which means that those 3 are connected together. And as a matter of fact, L, V, W were shot by barrel 2. That one, I and Y, shot by barrel 10, and that one, Q and Z, were shot by barrel 7. So it really helped to validate the key, and now you're way more confident if you are submitting it. Okay. So we have 4 distinctive groups right here. We can have a quick visual observation on the virtual comparison microscope. 2A, 2B, LVW. As you can see, there's a lot of good striator matching right here. If we wrote it, we have the other series of pair of leads, and that marks is really obvious. The other group, 7A, 7B, QZ. If you notice, we can look at more than two bullets at the same time. We can go up to 6. It is amazingly convenient. 9A, 9B, ANS. You can see that grooves right over here that is common to all the leads. And finally, 10A, 10B, I and Y, with that big grooves right here that is common to all the bullets. So, as a conclusion, quantum, there's 3 steps. Acquisition with a certified acquisition unit, viewing with 2 different modes, surface and shape mode, and we can actually get the chance or evaluate the chance of making a wrong call. Traceability will be done through the acquisition of certified golden unit. We explained the model that is behind the objective identification, and we ended up with a graphic where we show a separation line at false match rate 1/10,000, but we also have a series of ISO line that gives numbers to experts to actually support their conclusion if they actually go in court. And we resolved 2 simulated murder cases, and we resolved the proficiency from the MBH test using quantum. And it pointed out the fact that there was a strong consistency between what we observed on the virtual comparison microscope and the location of collision score in the objective identification graphic. I think this point is really powerful. And next, well, we will manage other calibers and materials in the next version, and eventually we will analyze other objects. Thanks for your attention.
Thank you, Danny. That may have seemed like a lot of information to digest, but it does reveal how powerful quantum can be in providing more objectivity. So next, I'm going to wrap things up with data management. All the data and outputs from those acquisitions, visual comparisons, and quantitative analysis are captured to form the work product. And they can then be used to produce reports or whatever documentation is needed. So the quantum application lets you organize and share the information and results. Throughout the quantum application, notes can be entered for each acquisition, comparison, and analysis. Also, general notes can be written at the workspace level, so it is easy to keep track of everything. This allows the work product to be built as the work is performed, and the notes always follow the data. As I mentioned earlier, all the data and the results are organized in workspaces. This makes it easy to manage the stored data because all the files are saved inside an individual workspace folder. You can browse the workspace files directly, such as with Windows Explorer. This also makes it easy to transfer a workspace by moving the workspace folder onto a network, an archiving system, or whatever area where you need to store your work. Now, data sharing. The 3D acquisition data can be exported and imported in a variety of native formats as well as the emerging X3P format. Transferring or sharing the 3D data can be done for collaboration on projects or for peer reviews, or the data can be exported for further analysis on external systems, such as for validation studies. There's a great benefit in working with 3D acquisitions because they're easier to transport than physical objects. Another example is standard 3D training sets that can be assembled and replicated to multiple students. Acquisitions are done on the workstation of Quantum. The workspace files can be stored or archived on the customer's network, like I just said. There's also an option of adding Quantum application extensions. These extensions allow firearm examiners to work at their desk by opening their workspace files on their computer. They can perform comparison viewing and quantitative analysis, and they can capture the images and the results that they need, such as to prepare reports and testimony. These extensions are especially useful for a divide and conquer approach, as it avoids taking up time on the Quantum workstation for analysis work when acquisitions could be performed for other cases or projects. If there is an IBIS bullet tracks acquisition station used for bullet entries onto an IBIS search network, the acquisition equipment can also be used as part of a Quantum 3D microscope. This can be advantageous if the dual purpose use of the equipment can accommodate the volumes of IBIS bullet entries and of the 3D microscope casework. So in a nutshell, the Quantum 3D microscope is useful for casework and studies related to firearm and toolmark identification. Now, we'll take some time to answer questions. All right, we have a first question here. Let me see. You said that the scores are computed by averaging over the best 2 leads. What do you do for fragments with only 1 lead? Danny, I think this question better be answered by you. That's your area.
Yep. In the conference earlier, I explained that our model is optimized for the average of the 2 ISD score at the best phase. Okay, this is why we call that the best phase mode. Okay, but we took the problem a little bit differently as well, because now if we take, let's say, 2 bullets with 6 leads, now we do not consider the best phase. We only compare all the combination of pair of leads. So we will have 6 times 6, we'll have 36 pair of leads comparison. And now we pick the highest scores among that. So we have a different mode that we call the best lead mode. And by doing that, we can actually work with fragments that only have one lead to compare. Okay. In Quantum, we have side-by-side 2 graphics, one for the best phase, the way I actually explained it today, but you have the best lead mode, and it actually has its own separation line and its own series of false match rate ISO lines. Okay, so when you only have 1 pair of lead to compare, you actually go in that graphic and you will have all the stats you need to draw a conclusion as well. Okay.
All right, another question here. What is the size limit for the objects that can be acquired in Quantum? I assume this question refers to the physical size of the objects, not the file size. So I think, Andy, you can answer this one.
Yeah. While I was acquiring different shapes, one of the items I put in there was actually a Canadian $2 coin, and that had a diameter of about 28 millimeters, which I think translates to just over 1 inch or so. When that was put in there, the focus was raised up to the maximum height, and that was just fitting in there. So a height of just over 1 inch, say 1.1 inch or 28 millimeters is the maximum diameter that it's able to digest right now. As far as when the door closes behind the exhibit, I think we've had 50 BMG in there, about 2 inches or so, about 50 millimeters in length would be as long as a physical, like the physical length of the exhibit could be when entered in the machine.
All right, thank you. Another question here. In addition to the false match rate, did you develop a model for likelihood ratio, as is covered in your published paper on objective identification? I think I'll let Danny answer that, but let me just show you a slide here in case you need to refer to the scientific paper. The information is here on the right.
That's an excellent question.
Yes.
I like the ratio. It's a challenge because it is computed from two different distributions, the null matching score distribution and the matching score distribution. The false match rate is computed with only one distribution, the non-matching distribution. So like I said earlier, we have much more non-matching score than matching score. In our case, we have 80,000 non-matching score, and we only have 235 visual matching score. So that's the reason why, because for statistical distribution to be valid, it must be generated by a really high number of scores. So that's the reason why we decided to focus on the false match rate for the moment. But we might consider actually computing it, the likelihood ratio in the future version, because if it is required by the community, we will actually provide it. Okay, but like I said, because it requires so much data, for the first version, we decided to actually stop on the false match rate evaluation. That's it.
Thank you. There's actually another question here about the false match rate. The question is, how was the false match rate validated? And there's another one also. It says, how reliable are the values like 1/100 million in the false match rate?
I was expecting that one. For score that actually are below the separation line, where we had the false match rate of 1/10,000. Well, the false match rate is computed from real data because, like I explained, we had the line and there was 8 non-matching score above the decision line, but we had 80,000 below that. So that's a real measurement. It's a direct measurement. But for a score above that separation line, but we have to extrapolate based on the behavior of the largest non-matching score, and we're using what we call the extreme statistics. This is usually used for insurance company to evaluate or even extrapolate the chance of a flood or a pending, for example. But details of this methodology is given in the paper. I think we have 2 or 3 pages on that. Okay, and for the geeks, okay, we have a standard method that we call bootstrap to evaluate the error on the computed false match rate. Okay, it means, as an example, if we have a false match rate of 1/10 million, okay, it means that the real false match rate will be in a factor of 10. It means it will be between 1/1,000,000 and 1/100 million. It's like an interval of confidence, and we evaluated that based on the bootstrap method. But that one is for geeks.
Or Danny, stay on. I think there's another question for you here. It's about the resolution of the system. There's actually a few asking about that, about pixels and Z depth. Can you answer that one about the resolution of the system, please?
Well, the resolution actually is 3 microns per pixel, and the depth resolution is about 0.3. And why we use that? Well, we believe that, I think it's a good point. We believe that for efficient use of the virtual comparison microscope, the field of view must be about 3 millimeter wide. Okay, and there's other reasons, because I've been working on subclass misidentification, and you need wide field of view. Okay, so with that criteria of wide field of view, and based on our hardware we have, the resolution of 3 micron per pixel is enough. And we actually show that in our paper. It is possible to do objective identification with this pixel resolution and with that depth resolution of 0.3 microns. That's it.
Okay, thank you, Danny. A couple questions here. Do you have quantum microscope for cartridge cases? And there's also questions about cartridge cases here. Why did you start with bullets and not cartridge cases? Those are very good questions. I'll take those. Basically, implementing the quantum 3D microscope for bullets was the first step, but the cartridge cases would be the next logical step. And the next model actually that we'll build will be specialized for those cartridge case, the head stamps, the heads, or the primer impressions, and other large flat objects that have impressed or striated tool marks. We don't quite know yet when that will be ready, but we've already started work on the more complex components that requires. The reason we started with bullets is because years ago, we made some scientific breakthroughs, and it was inspired by the greatest need, basically, of some of our customers that had difficult cases that involved bullets and that were difficult to examine under the comparison microscope. And that's why, basically, we started with bullets. But cartridge cases is the next big step. Let me see. Question here. I'm in the US. Would quantum be on NIBIN, which would block access to my files? Well, I understand that question. On high security IBIS search networks, NIBIN is one of them, definitely in the US. The security requires USB ports to be blocked. So you don't really have access directly on that computer to the files you have. But that's not the case for quantum. It should not be part of an IBIS search network. It would work more like on the agencies or the laboratories network. So there would be no issue there. If it's a dual purpose system like I described a few minutes ago, we'd have to work with like program entities like the ATF or NIBIN to ensure that the quantum product is separate from IBIS and that its files are available to you. That remains to be worked out, but it's intended to be, you know, on two different sides, basically. Let me see another bullet tracks. Thank you. What's that? I have an old bullet tracks purchased in 2011. Can I add quantum to it? Unfortunately, no. Quantum is based on new technology. For example, like was described, there's a larger field of view that you can see, and which helps for other techniques that, for example, one that Danny developed about, you know, detecting subclass. But you know, be aware that there are upgrade options to migrate to the new bullet tracks. There's another question here. I have a new bullet tracks machine. Can I use quantum? Okay, that's the reverse of the other one, I guess. Yes, you can use quantum with that bullet tracks machine. We just need to retrofit the equipment with the proper calibration targets that Andy described. So going forward, any new bullet tracks that we build would be able to do like dual purpose with the quantum because it would already be equipped with those calibration targets. Okay, we're almost done here. Next question, how many bullets can be viewed in the comparison viewer? Andy, I think that one you should answer.
Sure, yeah, I did not show that myself in my portion, but you probably saw it later on in Danny's. You can have up to 6 bullets compared simultaneously for visualization there. You'd have your reference and up to 5 test exhibits can be lined up. And when you do so, actually you have hairlines, movable hairlines between each one. So you can trace features across the whole sequence of those exhibits when you're doing a comparison between multiple exhibits like that.
All right, thank you, Andy. Question here, okay, again, calibration. You mentioned calibration using ISO 17025 certified targets. Could you tell us more about how we would verify the microscope's calibration? I'll quickly answer that one. Yes, like Andy described in this segment, the quantum 3D microscope will have certified targets. These have serial numbers and they'll be traceable through our suppliers who are ISO 17025 certified. We'll issue a calibration report with the system actual measurements compared to the calibrated measurements. So from that, users will be able to perform calibration checks to validate the measurements. And each 3D acquisition, you know, that acquisition data will be linked to the last calibration check information so that they can be, you know, traced, each one of them. And like Andy mentioned, beyond this calibration approach that we have on the microscope, you can acquire your own reference targets and export the 3D data and analyze it to do your own validation if you need. But be aware that 3D standards, they're not official yet, so that will evolve and will adapt as standards are published, you know, and if there's standard targets, we'll integrate those. So this is a good start. Let me see. There's a question here. Do you see 3D microscopy replacing conventional comparison microscope? I think that's a good question for you, Ron. I'd really like you to explore that one.
Sure, Michelle, I'd be happy to. You know, I anticipate a fairly lengthy transition actually before that happens. As examiners, our criteria for identification is based on a data set that's been pretty much acquired using light microscopy. And virtual microscopy involves much more data and in some ways different types of data. So I'm thinking that our internal databases upon which our criteria for identification is based will have to be, in a sense, recalibrated a bit. I will share, though, that once the courts understand an objective quantitative model is available, I'm suspecting that there's going to be pretty increased demand for it pretty quickly. So I see these two technologies, like comparison microscopy and virtual microscopy with the quantitative model, existing side by side for some time.
Thank you, Ron. So there are other questions, but we're running long a little bit and didn't want to extend it too long. So what we'll do, we'll gather the questions that you have and make our answers accessible on our website. Also note that this is being recorded, and the recording of the presentation will be made available next week for you. If you have individual inquiries, we encourage you to use our, the various contact channels that we have listed on our website, and we'll be happy to follow up with you. Also, if you're interested in a quantum trial, please contact us. We'll be happy to follow up with you with that as well. So in closing, I'd like to thank my colleagues Andy Boyle and Danny Roberge for speaking today, as well as our guest speaker, Ron Nichols, for his insights and contribution. On behalf of all of us at Ultra, we thank you for joining us today. Be well and stay safe.